Good evening, ladies and gentlemen. I'm Siddharth Kalam. This is slight change. So I'm doing my master's in metals and energy finance. It's in one of the courses in Royal School of Mine. So before starting this presentation, just a brief question. Why am I doing this presentation for? Like, just imagine a mining the operation is very expensive. Like, imagine you have invested tens of millions of dollars in a mine, bought very expensive equipment, trucks weighing 120 tons, loaders, and all that stuff. And just imagine those equipment are not working according to your expectations, just breaking down again and again. That quite hampers the production. For every percentage decrease in the availability of the equipment, that could mean a loss of thousands of dollars to the mine. So that's a very important topic that mining industry came up in the last 2 decades. So why the risk-based maintenance planning? So this concept was, so this is the presentation agenda I'll be going through. So risk-based maintenance planning, I'll be showing one of the proof of concept case studies. So I did during my work experience. I had a lead and zinc mine at Vedanta Resources in India, and one in the Mandalong coal mine in Australia. So there are 2 case studies, and then the significance. What are the significant results? So for the risk-based maintenance approach, this concept was thought of in the 1960s by chemical and aerospace industries in US and Europe when they were suffering from this dilemma. Why the equipment? How can we change the approach from reactive to proactive? Like, how can we make ourselves ready for the maintenance planning? And then they came up with certain techniques so that they could actually streamline all their resources, all their research towards certain critical factors which can save them a lot of money. So this approach was adopted by the mining industry in the last 2 decades and actually helped a lot. This approach, as in we applied this in one of the case studies which I'll be showing, and guess what? We saved around 250,000 pounds in a year. So that's like a lot of savings. If you see only for the LHD fleet, that's like 13 equipment. So that's savings for a year in the LHD fleet. So I'm not talking about other fleets that could like that we were to do, but like I'll be only sharing I'm only sharing the results for the LHD fleet. So this is the flow diagram, like how the basically risk-based maintenance approach works. So we kind of divide the system into the manageable units, then conduct a kind of result analysis of how can we segregate those units into, and then based on those units we calculate what are the frequency of occurrences of downtimes and what are the consequences on the productivity or the profitability of the operations are. And based on that, we calculate a risk factor or risk evaluation that we do. And finally, we come up with the approach to segregate those factors. And then we again follow the process and change or tweak our process. That's how this whole. So this for the first case study, this is a Mandalong coal mine in Australia, which I had an internship for 3 months there, and during this. Gained a lot of exposure of how they used to collect the data and reconcile it, and used to change their maintenance approach. So some of the facts about it. It was a long-haul coal mine operation, 6 million tons. It used to produce by long-haul system, and from transportation from the mine to the surface was to the conveyor belt. Fleet maintenance was carried out by the maintenance team at the mine, and the maintenance procedure was like 2 shifts of 8 hours every week. So the features of the system which they followed was that it used to produce a report, this 12-page report every week, which used to give production statistics about the rates, equipment, processes, locations, everything about the mine, what production activities going on, operation hours, cutting time, what are the downtime which occurred, productivity measures, utilization, availability. this 14-page report that was like my manager. It used to be like in the hand of my manager, and he can take decision what we have to do in the next week. So it's like a very advanced system that they came up with, which worked like that. The mining machinery used to produce the data, which used to go through the fiber optical cables to the surface, and from there it used to store in the SQL database system, and they were actually, as in the joint venture of the Pulse Analytics system, they used to produce this report which used to give them a segregation into monthly, daily, and weekly reports. So that's like a lot of advanced data analytics they used to go with. So this is the second case study about the SK mines, the lead and zinc mine where I worked for a year. So it was a cut and fill operations, 6.5 million tons. The mining equipment was drill and blasted through drills loaded by the LSD, the load haul dumpers, of 17 tons, and brought to surface by ramps by mining trucks of around 70 tons. Fleet maintenance was carried out by the original equipment manufacturers. In this case, it was Sandvik and Atlas Copco. So they used to maintain their own fleet. And the maintenance procedure was based on the time base, like after every 125 hours, 250, 500, and 1,000 hours of engine runs. So that's the how the data used to flow. So we used to engineers used to produce everyday daily shift report about how the operations went and which equipment went down. And separately, the parallel DSR was used to be produced by the original equipment manufacturers. They used to reconcile both DSRs to produce the final DSR, which used to give the exact numbers, and that data used to go into the database. And that database was used to come up to us as an asset optimization team, and we can transfer that data to our managers who can take certain decisions of how we have to deal with the approach and how to move forward. So this was the DSR, which, like as an example, the Sandvik used to produce. So you can see that what are the reasons of breakdown, the total breakdown hours, is the washing breathing done. So these were like how the checklist used to produce what are the engine hours. So that they used to do it every shift. So that and based on the DSR which we used to produce, we produce the final DSR. After that, we used to. So this was the approach we started after certain experiments. Whether we link the equipment parts to the downtime factor. So like as a powertrain of an equipment which has a pump assembly, and in a pump assembly there is a certain hose. So if certain hose, if there is a hose puncture and what's the reason for the hose puncture is hydraulic oil leakage. So every of these factors are given certain tag numbers, and based on that we can actually relate. If someone has to detect what is the actual factor for the powertrain downtime in the hose, it's easy to find and analyze. So that was the approach we came up later in the analysis. So this was one of the efficiency projects which I said we did for the LSD fleet. So 13 LSD fleet were there for 17 and 20. We did for 21 ton capacity. So we determined the mean time between failures and mean time to repair for the primary categories of equipment downtime, which for the 6 months period which we chose for the LSDs. Based on that, we calculated the risk factor. So the risk factor I'll explain in the next slide was calculated based on this formula, and based on that we developed a Pareto chart so that segregating the most critical factors for the LSD downtime. So if you can see in the risk factor, the one upon mean time between failure gave us the hours which LSD is going down for, and on the right side of this formula gives what's the consequence or the impact in terms of the tons of hours lost by every LSD which goes down. So based on that, these factors, these are the primary factors which led to the downtime of LSDs, and we calculated the Pareto chart. And if you go back 80-20 rule, so we segregated only the first major factors which contributed to 80% of the downtime. So that helped us segregating those factors, and concentrating on them. Based on that, we determined the span and frequency of all the sub-factors between these primary factors, which, so it was further segregated as the sub-factors was determined, and their span of occurrence and their frequency of occurrence were calculated, and based on that we developed a bubble matrix which looks like this. So if you look all of these downtime causes, hydraulic oil, these are one of sub causes between those primary causes, and so this is the frequency of downtime, how many times they have occurred in last 6 months, and the span of the downtime, how many hours they have prolonged, and so we have concentrated on the region of high impact. So we shortlisted those downtime factors which are actually hampering the availability of the LHPs. So we concentrated on these factors, top impacting factors, and so we studied the DSR reports of last 6 months for the LHPs and determined what are the detailed causes of failures and analyzed what are the spares which are used for consumption or which are consumed to rectify these problems. So we went into the spare consumption details. So based on that, so this was for each LSD we did for like overheating downtime. What is the criticality factor which was calculated with multiplying frequency into the span. So we calculate for each LSD how the different sub-factors are impacting each LSD. So it helped us give us exposure of what are the factors which are impacting each LSD in detail. So this was the spare consumption model which you saw. So if you can see the spares which are used for rectifying those problems, for each LSD how many spares are used, what are the frequency of spares which were used, and the quantity of spares. So which helped us to determine that which of the spares were used for most and where were they used in the LSDs. And this was for the hoses similarly. So where those hoses were used, as in was there a boom and bucket hose or a steering hose or a transmission hose or a brake hose, and how many quantities they were used for in the last 6 months. So now then we went to the manual and checked where these hoses and O-rings are generally fitted, and then we determined that so this I'll be showing 2 of the examples which we went through, and similar to this, 13 such corrections were seen which would be implemented in the LHDs. So like if you can see in that part number 937037, there was a problem of improper torquing which used to occur, that sometimes maintenance person don't apply enough torque so that O-ring goes into the right place. So ideally it should be 3.5 turns, but due to sometimes in order to do it quickly, they used to do it improperly, and that led to a lot of due to vibration in the LSD, that led to breaking of joint at the point. And similarly for the hose, if you can see, so the hose which used to fail was because of the failure to high bending radius. So because of high pressure fluid that flows through the hose, so if there is a lot of vibration in the LSDs, so these hoses have to have a long bending radius so as to prevent the high pressure on the contact of the joint. So that led to a lot of rubbing and tearing of the hoses. So that was another reason we found. So how we rectified it? So for the first O-ring, what we said, we can make the joint as permanent instead of attaching it with O-ring. That would actually help rectify the joint problem. And for the hose, we increased the bending radius and circulated the hose from the downward part of the machine. So that improved the availability of the machines related to these problems. And finally, we came up with this alarms checklist. So what this checklist is for, that certain alarms refers to certain downtimes which I mentioned, which used to occur in every LSD. As in, if a machine has certain warning, it shows signal on the dashboard. So after every shift, the maintenance person can check the dashboard, and if there is the alarm of that, he can click on that, and after that, in the maintenance time of the machines, the maintenance team can work on that certain warning of the machine. So that help in proactive approach is with respect to reactive approaches. So the advantages of the maintenance planning is that it gives approach to the most critical downtime factors and helps streamline the focus of the mine management, and it provides edge in terms of priority planning and inspection. So it gives a lot of advantage in terms of we can plan beforehand and we can order the spares which are actually needed and critical for the equipment. So that improved a lot, and more focus was given towards research and like quality maintenance practices, where we can see how can we improve the design of the machine so as to satisfy the design of the mine. Thank you.
You certainly hit on an important point, equipment downtime. Has always been a major problem in mines. But what sort of productivity advantages did you gain from it?
It was like for the machines before this, we used to have like 40% availability in a month as an example, and if we went through this operations, and that availability was improved to 65%. So that 25% gain in